Okay, this is the initial and boundary condition for heat equation. Let us go through some points given here. One cannot just add any set of conditions. The second thing mentioned here, they should be chosen such that the problem is well posed. Well posed means we have a solution exists, unique, its behavior changes continuously with the initial conditions. So in order to obtain a unique solution, one needs to specify additional conditions, usually one for every derivative. So one for every derivative here, is explained based on these 2 points below. So as we can see from the heat equation, there are two terms. First, we have del U del T on the left, and second term is del square U del X square on the right. Okay, so actually, here is the first derivative. So based on this, we have one condition for this. Okay, and another term is del square U del X square. Second derivative, actually we will have two conditions. Okay, so since the heat equation contains del U del T, we usually add an initial condition such that U x0 equal to Fx. So this is called as initial temperature distribution. Okay, this mathematically written like this: U at point x, any x, the value for t is equal to 0. The right hand side Fx. So here can be constant, can be any function of x. Okay, U is the temperature. So at time t equal to 0, so the physical meaning is t equal to 0 means initial. The term U here is the temperature, so physical meaning is initial temperature for this condition, the initial condition. Okay, initial condition because it is the condition at time t equal to 0. Here is the range that we have for x. For example, we have x from 0 to certain number L. While for the del square U del X square term, in this course, we will consider two types of boundary conditions. First is control and temperature. I think in some reference, they name this as Dirichlet type. And the second one is insulated ends, if I'm not mistaken, named as Newman type. Okay, so for the control and temperature, means it takes the temperature. Okay, the condition, the boundary condition is about the temperature. So the term is U, okay, because U is the temperature. There are two conditions. First at point x equal to 0, and another one is at point x equal to L, or we say at both ends of the rod. Okay, so in general like this, U0T equal to UB1T, and the second one ULT equal to UB2T. So there are some more cases based on this type. It can be both 0, like we see in the example for the method of separation of variable. The first example that we see is both are 0 value, or called as 0 temperature at endpoints. Okay, it also can be values both at both ends, constant. So far, I've seen the type 0 temperature at both ends, contains constant at both ends, or one of it constant, another one is 0. But if I see here, there is bracket T t means it also maybe in terms of t function. Okay. So for the control and temperature, when both temperature at endpoints equal to 0, we have seen in our first discussion about method of separation of variable. The second type is insulated ends. Insulated ends, we have to consider the heat flow. Okay, heat flow or flux. Remember, in our formulation for the heat equation, we do have the assumption, and we have this expression phi, the flux, is equal to negative k naught del u del x. So when we have the insulation means there is no heat flow or no flux. So this implies that del u del x equal to 0. So here is the explanation why do we have del u del x equal to 0. Because when the case no heat flow, means that we have phi equal to 0. So when phi equal to 0, taking this expression, we substitute phi equal to 0 here. So we have negative k naught del u del x equal to 0. So k naught is constant. That's why we have, for this case, del u del x equal to 0. So therefore, we consider del u del x equal to 0 at both ends of the rod. For the first end, at point x equal to 0, so we have the boundary condition del u del x 0t equal to 0. And at the second end of the rod, we have del u del x at point x equal to L, t equal to 0.